All right. So we're going to start out just with some basic information about carbon, right? Because that's what organic is. It's the study of carbon and carbon containing molecules. So we're going to start out with some basics, just kind of a recap of what some of the stuff that's in the video. And then we're going to, if you have had a chance to download the handouts from modules 1 and 1A, that's great. If not, you can grab them at any time. They're both located in the assignments folder within the module. So today we're going to discuss if I can get my iPad to act right. Really, bro? What are you doing? I don't know why my screen is acting dumb all of a sudden. But we're gonna get it together. So we're gonna discuss carbon, the geometry, how it bonds. What else do we want to talk about? We're going to talk about some structural representations. And if we get a chance, we'll get into hybridization, because that's a very important topic. And all of this stuff, if you watch the videos, you've at least been exposed to it. You may not know exactly, have a full, complete understanding of it, but you've seen it. But my brain is not working. All right. So we're going to get into all of these topics. And all of these are different. These are the handouts that we're going to be working from. So from module 1A, and then we'll do the skills as they come up, right? Because there's a lot of information, preliminary information that we need to get out before we can like dive in and just start working. Because some of this stuff may be new to you and some of it may not. Some of it you learned in 232, which is the second part. You either had Dr. Reeves or Dr. Biswas. So let's start out talking about carbon geometry, right? And then if you watch the video, the very first video, the introductory one, right, it talked about carbon existing as I'm just going to put all hydrogens on here, tetrahedral. Right, it's a tetrahedron. So it has this tetrahedral geometry, and it has the angle between the atoms, which we call the bond angle or dihedral angle between the atoms is 109.5 degrees, right? Now, this is important. Let me just go ahead and say this. We're not going to talk about skeletal and line structures yet, but this is why when you draw a skeletal structure for carbon, like if I had a carbon chain that looked like this, that was 3 carbons, let me do 4 carbons. Right, normally when we write out the Lewis structure that looks like this, we write out all the carbons and all of the bonds to it. But when you write this in, let me zoom in on that. This is Lewis, and then this is going to be skeletal. This is why we write it as a zigzag, right? Because every carbon in that chain is actually a tetrahedral. So we don't write it like this with 4 dots on a line, right? We actually write it the way it would actually, the way it's actually shaped, which is as a, with each carbon having that tetrahedral geometry. All right, are y'all following that? Does that make sense? Yes, no? And
Yes.
feel free to interrupt anytime you have a question. I can't, well, I can see it here, but you don't have to raise your hand. You can just unmute and ask. I have no problem with you asking questions in the middle of a discussion. So please do so. But this is why we write it as a skeletal form, because of the geometry. But the interesting thing about carbon is that it can adopt different geometries based on what is bonded to, like how many bonds it has to it, right? How many bonds can carbon form, period? What's the maximum number of bonds it can form? Anybody?
4.
I heard it, but can you speak up a little?
4.
4. Maximum number of bonds is 4, right? You have some special cases where carbon may have 3 bonds to it, but under normal circumstances, a neutral carbon is going to make 4 bonds, right? So let's go ahead and get that established up front, so you don't put something on a test with 5 or 6 bonds to it, and get, like, you know, a really bad comment back from me. Not real bad, but you know, no cussing or nothing, but a little bit. So it can make 4 bonds, and depending on what type of carbon it is, what the hybridization state is, which we're going to talk about later, it actually can make double bonds or triple bonds, or they can be all single bonds. So we can have a carbon, and you, if you watch that introductory video, you've seen this already. It can have 4 bonds to it like that, or it can have 4 bonds to it like that, where it's double bonded to another carbon or another atom. Doesn't always have to be carbon. Or it can have 4 bonds to it like that, right, where it's triple bonded to another atom. Either way, it's going to have 4 bonds. If it doesn't have those 4 bonds, there's 1 or 2 exceptions, right? It's either going to be a cation or it's going to be an anion. Those are the cases where you'll see carbon not having 4 bonds. So if it's a cation, let me show that. That means it's positive, right? You've heard that term before in Chem, as it relates to a positively charged atom. Yes, I will. The lectures and the notes will, everything will be, the lectures video will be on YouTube, and then the notes will be on Blackboard. Yes. Great question. All right. And also that same carbon, we can have like this with 3 bonds to it and a lone pair, and it's negative, right? That's an anion. All right, so let me touch another topic, which is very important, and everybody needs to know how to do it. It's a skill that you can't live without in this class, because you're going to see it from this point forward, which is formal charge. Let's talk about that. And then we're going to come back to the different representations of carbon, line structures, Lewis structures, all that type of stuff, skeletal structures and things like that. So let's talk about formal charge. Right, so that's the charge on the atom. It's either going to be positive or negative. And since we're dealing with carbon and not a metal, you know, metals can be +1, +2, +3. They can have different oxidation states. For carbon, the formal charge is either going to be 0, which is if it has a full octet and it has no extra electrons. It's going to be +1, like the cation that we see here, or it's going to be -1. So the way we calculate that is to take the valence minus actual, right? That's how we calculate it. Very simple. When you did calculated charges in general chemistry, you probably did something like the valence minus 1/2 of the bonding electrons, yada, yada, yada. It's the same idea, but it's just simplified. So when we look at look at the cation. Let me do this. How many electrons are in each bond?
2.
2. Good. There's always 2 electrons to make up what we call a covalent bond, which we're going to talk about also. Right, so it's 2 electrons to make up a covalent bond. So every one of these bonds has 2 electrons in it, right? When you're calculating the formal charge, let me just write this in. When you're calculating the formal charge, what you are looking at is the valence, which you can tell from the periodic table, right? So for this molecule, the valence is going to be 3. I'm sorry, 4 for carbon, right? If you look at the periodic table, carbon has 4 valence electrons, right? And then the actual will be the electrons that are around it. So in this case, you have 3 electrons around that carbon. Even though it's bonded to 3 atoms and there are a total of 6, the actual are the electrons that belong to carbon. That's where the 1/2 of the bonding electrons comes from in the other formula. But here, if we see 3 bonds, then there are 3 electrons around it, actually, right? So that'll be 4 minus 3. That's how we arrive at the +1 formal charge. We're going to do this a lot more, so don't panic if it's not clicking right away, because we got a lot of examples where we're going to calculate formal charge. All right. Any questions about that? All right. Let's look at the anion. What's the valence? Again, valence minus actual is how we're going to calculate that -1 charge. Valence is what?
4.
4. What's the actual?
5.
Good. 5. Right? Actual is 5. You got 3 from each one of the 3 bonds, and then you have a lone pair. That's 2. Even though sometimes we like to group them together, that's 2 electrons on that carbon. All right. And so that means that the formal charge is going to be, in that case, -1. Any questions about that?
Is that what makes it the minus, the anion, because it has 5, so it becomes
Yes. So it has an extra electron, right? In addition to the 4 valence electrons that it would normally have, it has an extra electron. That's exactly right. And so what the charge on an electron is negative. So anytime you have an extra electron, is going to increase the charge to -1, right? If I add 2 more electrons, then the charge would go up to -2. I can't do that here because it'll violate the octet rule. But the point is, every time you add an electron, the charge is gonna become negative by a factor of 1. All right, great question. All right, any other questions related to that formal charge? I just felt that that would be a good place to talk about that. All right, any questions about anything? All right, so let's add another layer to this and talk about like how carbon makes bonds, right? We know that there are 2, you learned about 2 types of bonds and let me put a heading up here. So when you go back and look at this, you'll know what you're looking at. All right, you learned in part 1 about the different types of bonds, right? That there are what we call ionic bonds, which is really not a bond because there's no shared electrons. It's more of an attraction. So I'm going to call it. Right, you learned about ionic attractions, and that's just something positive being attracted to something negative. Or in this case, if I wanted to use real atoms, something like sodium chloride, that's an ionic attraction. That is, out of all of your bonds or bonding types, this is the strongest attraction, ionic. But then there are also covalent bonds. And those bonds are called covalent bonds because that word co, or the prefix co, means share, right? So what this means is that this is a bond based on shared electrons. Right, or shared valence, overlapping. I'm gonna talk about that, right? So a covalent bond is a bond based on where electrons are shared between two atoms. Right? So carbon can make these covalent bonds, and they can make different, it can make different types of covalent bonds, right? It can make single bonds, it can make double bonds, it can make triple bonds. And that's what makes carbon so versatile, because of the way that it's able to bond to itself and bond to other atoms as well, right? So when you think about something like, let me just write ethane. Want to write it in Lewis form, and then we'll kind of gravitate towards using more skeletal forms later, right? But this is a representation of ethane, which has 2 carbons in it, right? So the bond between, and I'm only going to focus on the carbon-carbon bond, the carbon-hydrogen bond.
Excuse me?
Go ahead.
What does it say beside number 2 in front of it?
Between, right
Thank
here.
you.
Yeah, it's just an abbreviation. Let me fix it though, because my W is kind of suspect. So it's just a bond based on shared electrons between 2 atoms. Right, so we're only going to focus on the carbon-carbon single bond, because that is a, the carbon-hydrogen bonds are also covalent, but I want to focus on the carbon-carbon single bond because it's going to allow us to segue into hybridization, all right? And so ethane has this carbon-carbon single bond, or we call it a sigma bond. Right, that's the result of overlapping orbitals. Right, that's how carbon makes bonds with itself and other atoms through the process of orbital overlap. This is very important because you're going to see this a lot. And you're especially going to see a lot of this when we start getting into different reactions and things like that, because that's how atoms interact, right? Especially when we're talking about organic chemistry and the different reactions of, carbon containing molecules. Everything is based on orbital overlap, right? The better the overlap is, the tighter or stronger the bond is. The worse the overlap is, then the bonds become weaker and more loose. All right, any questions so far? Let me know if I'm going too fast, or you need me to pause, or if you have a question, just interrupt. Feel free. All right,
I have a question.
go right ahead.
What does it say? That says CCO
Sigma bond.
bond?
It's a sigma.
Oh, sigma bond.
Yeah, lowercase Greek s.
Okay. Thank you.
Mhm.
So if it's a sigma bond, will it always be overlapping?
Yes, all bonds, covalent bonds, are the result of overlapping orbitals. Right. Every bond is a result of a orbital overlap. If it's a covalent bond, if it's a ionic attraction, then it's just electrostatic, right? Positive is attracted to negative, and that's what's holding those 2 atoms together. But if it's a covalent interaction, then it's always going to be orbital overlap. That's how you that's how you make bonds. So let's talk about that real quick. I'm glad you asked that question. This is a good class too. I can already feel it, which is a blessing. It's been a long summer. So to jump back in and have a good class to come to, that's great. All right. So let me talk just for a second about valence bond theory. Right. And a lot of this stuff you've heard, right? You've heard this in Chem part 1. We talk about valence electrons or outer shell electrons. Those are your electrons that are used to make bonds because they're furthest away from the nucleus and they're more readily accessible, right? So let's think about carbon, and let's think about the atomic number of carbon, which is what? Anybody?
6.
It's 6. And the atomic mass is 12, right? So carbon has 6 electrons. And do y'all remember from part 1 in Chem where you had to learn like the Aufbau buildup? You learned about orbitals and Aufbau buildup and Pauli exclusion principle and Hund's rule and all of these things. Do y'all remember what that applied to? If you got an A or a B in Chem, you should be snapping that off. I'm just joking. Well, somewhat. Anybody? All right. Remember how for carbon it has 6 electrons, but it's got only 4 valence. And that's because if you do the Aufbau buildup, you'll remember it when I start writing it. It's 1s, 2s, 2p. Y'all remember that?
Yeah, I
Yeah.
remember that.
Yeah.
So it's 1s2, 2s2, because you can only fit 2 electrons in an s orbital, and then 2p, 2. Yes, that's a total of 6, but you have 4 valence. I'm not going to write it on that line because it's going to get cut off. Get your handwriting together. All right. If you hear me mumbling to myself, don't worry. That's just how I motivate myself to write better. Because my handwriting is atrocious. I'm humble enough to admit that. All right. So you got 4 valence electrons, 6 total, right? And again, when we talk about valence bond theory, right, what we mean, what valence bond theory says is that 2 atoms, when they come close enough together that their valence shells can overlap, that's how they make bonds. So let me write that down. All right, so bonding occurs. Here's my abbreviation for between again, between 2 atoms when they're close enough for their valence shells to overlap. All right, are we following that?
Yes.
All right. So when those atoms come together, the optimal distance between the 2 atoms, that's what we call the bond length. So when we say come close enough, that means they're at the optimal distance for bonding, and we call that the bond length. So the optimal distance for overlap, we call it the bond length. So can somebody Google real quick, because I know you got your phone close by somewhere, the bond length for a carbon-carbon single bond or sigma bond? Anybody, real quick? It's either going to be an angstrom.
It's I got 154 PM.
Picometers, 154.
Yeah.
Right, that's 10 to the minus 12. So 1 154 times 10 to the minus 12 meters. It's a very small distance. Sometimes it's also measured in angstroms, but picometers, that's fine. We can use that too. All right. So in order for, let's go back to our molecule up top, ethane, right? In order for those two carbons to come together, what has to happen in this particular case is, well, two things, but I'm just going to draw a generic. So you have an electron here, and then you have another carbon on the other side with an electron here, right? And those two orbitals overlap. And when they overlap, that's how you form a covalent bond between those two atoms, right? So once, because here's the thing about those, when we say orbital overlap, as long as the orbitals, and I'm gonna talk about this in 1 second, have the same sign, then it's gonna be what we call constructive overlap. So they're gonna add together. That's why you don't see it separate. That's why you don't see the two separate orbitals anymore once they add together. So this is, I'll put constructive up here if I can fit it in. More than one way to skin a cat. So this is constructive overlap. Right, that's what you get when you take two orbitals and you overlap them to share electrons. You get what's called constructive overlap. Right, and I'm gonna talk about why it's important, the term constructive versus destructive, because if the orbitals don't have the same signs, then they can't overlap. So let me backtrack. We go back down here. Right, so this is an example of valence bond theory, where two carbon orbitals they come together, they get close enough to overlap, they overlap, the orbitals combine, right? And you get a covalent bond. That's what this is an example of.
I have a question.
Go right ahead.
When you're writing like the 1s and 2s2 and 2p2, is that coming from the periodic table?
Yes and no. It's coming from the periodic table because the numbers that I put into the orbitals, right? The number of electrons, we get that from the periodic table. But
Yes.
the actual buildup is what's called an Aufbau buildup, right? It's the standard method for building up an electron shell or electron shells for atoms. So it's 1s2, 2s2, 2p2, 3s, 3p, 4s, 3d, so on and so forth, all the way up to 7f. Right? Let me write that down right here. You can actually look it up. It's called an Aufbau buildup, and that's how you construct your shells for any atom, and it's based on the atomic number, right? However many electrons it has, that's going to determine the number of shells, because every orbital can only hold so many electrons, right? So the S can only hold 2. The P, because there are 3p orbitals, which we're going to talk about shortly, it can hold up to 6. The D, there are 5d orbitals, so it can hold up to 10 electrons, right? Let me show you that down here. Do y'all remember the shapes? Like the S orbital is a sphere like that. And then the P is a dumbbell with a shaded side and unshaded side. And then the D has multiple shapes, right? But let me just write one. So you have a dumbbell and a donut. I don't know if y'all ever talked about that in Chem, but you have a dumbbell and donut. And you also have, right, a d orbital that looks like that. So there are like 5 different d orbitals, right? dx, dy, dz, dx squared minus y squared, and dz squared, right? So S can hold 2 electrons. And then P, you have, let's say, let me say this is Py. Py, Px, which is going to be along the x-axis. And then Pz, just say along the z, because it's based on the Cartesian coordinates, right? The x, y, and z axis. So with the S, it can hold 2 electrons. With the P, you got 3 orbitals, so you can hold a total of 6 electrons. And then with the D, it can hold up to 10 electrons because there are 5 orbitals. All right, any questions about that? So these are, when we talk about orbital overlap, this is what we mean. Let me ask this question, because since we're talking about orbitals, this is also another important like concept dealing with orbitals. Like, what is an orbital? Can anybody tell me that?
Is that like how the electrons are surrounding the nucleus?
Okay, I'm with you. It's a depiction, right, of the path of that the electrons take around the nucleus. Yes, right. An orbital is a graph. It's a graph, a very high level graph, but it's a graph of the path of an electron. Right? Depending on what type of orbital it is, that's going to determine what the graph looks like. Right? So again, the S, the P, the D, and the F orbitals, which I didn't put here, but I'll put up here. There are 7 Fs. They can hold a total of 14 electrons. Right? So the orbital is actually a graph of the path of an electron, like the path it takes around the nucleus of an atom. Is not real, right? That's one thing that we need to understand, is that it's not tangible, right? It's theoretical. So I can't go to Home Depot and buy like a box of orbitals, right? Or to Lowe's or to the electron store, right? It's not real. It's only an approximation of the path that an electron takes around the nucleus of an atom. So with carbon, and this is really important. So with carbon, what orbitals are involved? Let's go back up and look at the electron configuration. What orbitals are involved with carbon? If we look right here at the electron configuration, what orbitals are we caring about here?
I guess just the S orbital and the P orbital.
It's the S and the P. That's it. All right, very good. We only care about with S and P with carbon. So with the S orbital, we know it's a sphere, right? And it has a sign because it's an equation. Every equation has a sign, so this is S. With the P orbital, we know it's a dumbbell, right? And notice I have one lobe of that shaded and one lobe unshaded. And between those lobes, we have what's called a node, N-O-D-E. Right, that's a place where no electrons can be. It's a place where the graph of the orbital passes through 0. Right? So this orbital, the lobes have a sign. So we'll call this positive and that negative. Right? So in order for this orbital to overlap with another orbital, like those, the signs have to match up. Otherwise, it's gonna be not constructive overlap, but destructive overlap. I think I see, so where the electrons are organized is, was that an answer to a question, Shikari? Okay, all right, cool. Did I answer it? Or, yes, all right, great. All right, so here we have a s orbital and a p orbital, and those are your orbitals that are involved with carbon bonding. Now I want to show you in the last few minutes what all this stuff means, right? So let's take, for instance, you have, let's say you have a carbon that looks like this. I'm gonna draw it out as a tetrahedral. You have a carbon that looks like this. I just want to put hydrogens on it. And you have a carbon that looks like this. Fix that. All right. All of these are possible. And the reason that they're possible, there's a theory that discusses how these different conformations or of carbon are possible, right? Or how these different structures are possible. And that is based on everything we just talked about. It's based on orbitals, it's based on orbital overlap, and it's also based on the electron configuration for carbon. So let's look at that real quick. This is a topic that's really important, right? And it's called, the topic is called hybridization. So let me add a page, and then we're going to talk about that. So let's do that. And again, all the notes will be on Blackboard in a folder labeled course notes. So you won't miss it. Anything you don't get, you can go back and fill in the blanks, and you can rewatch the lecture also to fill in blanks, right? So hybridization is, for lack of a better term, if you watch that video, it is orbital mixing within an atom. How many of you watched that hybridization video? Two raised hands. All right, that's better than 3. Okay, that's better than 0. All right, so let's think about carbon, and let's go. We're going to write this electron configuration again, and I want to show you something that's very important. So we said that carbon has 4 valence electrons. Yes, is that right?
Yes.
Yes.
And we said the configuration, the electron configuration is 1s2, 2s2, 2p2. Everybody with me on that? So you got
Yes.
4 valence electrons based on this right here. But I want to show you something, right? Remember we said that the p orbital actually had that there are actually 3 p orbitals, right? So I'm gonna write this out. These don't matter because they're too close to the nucleus to matter. They're not valence electrons, so we don't care about them. So we only care about the 4 electrons in the outer shell. So 2s2, we know that's fine. We're gonna leave that how it is. But then also we have 2px, 2py, and 2pz. Everybody agree with that. We know that there are 3 p orbitals, and the x, y, and z is a reference to the axis that those orbitals, like how those orbitals are oriented along an axis, right? And so let me move this over. Now, how many electrons do we have in p again?
6.
No, in the p orbitals, how many electrons do we have? We got a total of 6, that's correct. But how many electrons do we have in the p orbital?
2.
2, good. So we got, and do I pair them? or do I fill them all with one before I pair up any? Y'all remember that from Chem? Hund's rule. You got to put one electron in each degenerate orbital before you put two in any.
Is that where you draw like the lines?
The little arrows pointing
Go
up
and
and
you-
down,
Yeah,
like that.
yeah, I kind of remember that.
Yeah. So we can't just put two in PX, right? Because PY and PZ have equal energy. So we got to fill the what they call degenerate or same energy orbitals up first before we can pair up electrons in any. So we got two electrons, one in PX, one in PY. How many? Now let me ask this question, and we're gonna close in a second. In order for an atom to make a bond with another atom, a covalent bond, you saw that up top. What does it need in order to make a bond?
The optimal space, optimal
Okay.
distance.
Need the right distance, and it needs some electrons. Is that right?
Yes.
Okay. Let me ask this question. If I only have two unpaired electrons, because you can't make a bond, right, with electrons that are already paired up because they're happy, right? They're not looking to be split apart. That's why the spins are opposite, right? And within a particular given orbital, you put two electrons in there, they got opposite spins, they are happy, they don't want to be disturbed. So in theory, if I look at carbon, and this is the electron configuration, how many bonds should it be able to make in theory? If bonds only happen between orbitals that have unpaired electrons. Because 2s2, both of those electrons are tied up. Am I right?
Yes.
So how many unpaired electrons do I have?
Two.
Two. So in theory, right, carbon should only be able to make two bonds. Is that right? Because it only has two unpaired electrons. Fix that. Does that make sense?
Yes.
No.
Okay, I heard somebody say no. All right. Let me ask you this question. Let's say that as a human being, you have two hands, yes?
Yes.
What if you clasp your hands together, are you able to hold hands with the person next to you?
No.
No, right? If you extend both of your hands, you can, no. Am I right? You can hold hands with the person on the left and on the right. Is that right?
Yeah.
Okay. What if you had two hands and four people around you? How many people could you hold hands with?
Two.
Only two. It's the same idea. You only got two unpaired electrons. So in theory, I'm saying in theory because I'm going to make this make sense and help to explain how carbon is able to make those four bonds. But in theory, there are only two hands. So it can only hold hands with two atoms in theory. But we're not going to rest there because that's actually a way to explain how we're able to make four bonds instead of two. And it's based on what we call the theory of hybridization. Right. So we're gonna stop here because we gotta stop at 10:50 according to the new rules. So we'll stop here. But what we'll do is pick this up on Wednesday at hybridization, and then we're gonna jump right into that handout and pull out some examples and work through them to apply what we've learned so far. Hopefully we didn't go too fast, and hopefully you got something out of this. All right, so I'm gonna write this down. All right, so it should only be able to make two bonds based on what we see. And based on the unpaired electrons in the valence shell, it should only be able to make two bonds. But we know that's not the case, right? Because at the very beginning, we said that carbon is able to make how many bonds?
4.
Four. And it's able to make those bonds in different ways too. Am I right? It can have 4 single bonds. It can have a double bond and 2 single bonds. It can have a triple bond and 1 single bond. So it just depends. All that's dependent upon hybridization, which we're gonna start the class on Wednesday with that. And then everything else, the polar covalent, non-polar covalent, all that type stuff, we're gonna get to as we work through that handout. Right. So we're gonna touch every one of those learning objectives. It's just not gonna be explicit. It's gonna be implicit based on what we learned today and the information we got today. We're gonna be able to apply that to multiple examples. So hopefully you'll come back Wednesday to get the rest of the good stuff.